Okay, so here we go with part 2 of solving applications of systems of equations, right? And as I mentioned, the two types of problems we did last time were cost problems and interest problems. This is the third type of problem. These are mixture problems. Right. Right. So here's the question. We have a chemist has a 9% hydrochloric acid solution and a 5% hydrochloric acid. This is the abbreviation for hydrochloric acid solution. How much of each should be mixed to produce 20 liters of a 6.2% hydrochloric acid solution? Okay, so again, first step is always make sure you understand the question, right? What are we looking for here? How much of each, right? How many liters of each, right? So how many liters of the 9% of a 9% hydrochloric acid solution do we need? So let's give that a name. Let's just call it X. All right. So let this be X. And the second question is how many liters of a 5% hydrochloric acid solution do we need? Let's try that one more time. Do we need, right? So let's call this Y. This amount. And you can see I'm getting lazy here, but if we should maybe write this out, right? So let X be the number of liters of the 6%, and you can abbreviate, right? HCl for hydrochloric acid. And let Y be the number of liters of the 6%. There's no 6% here. 6.2% is what we're looking for. But we only have a 9% solution and a 5% solution. So let's try that one more time, right? So 9% solution and a 5% solution. Okay, so that's what we have. And what we want to get, we want 20 liters of a 6.2% hydrochloric acid solution. Right. So yeah, we want exactly 6.2% of the 20 liters to be hydrochloric acid, right? Okay, so we're going to mix these two together, hoping to get 20 liters of the 6.2% hydrochloric acid solution. Okay, right, so step 2. Well, as always, make a table. Right? So what do we have? We have a 9% solution. We have a 5% solution. And when we mix them together, remember, we're not adding the percentages, right? We don't get a 14% solution. What we want for the mixture is 6.2% solution. Okay. Right, so what about the rows? The rows are, well, you have the amount of the solution. So a solution is really just a mixture of the hydrochloric acid and other stuff, usually just water, right? So what goes in the solution is the hydrochloric acid, right? So this is pure hydrochloric acid. mean, it's I guess it's never really pure, but it's, you know, almost essentially just pure hydrochloric acid, right? Okay, so, right, so for the solution, we're looking for X liters of the 9% solution, Y liters of the 5% solution, and we want 20 liters total. Right? Again, that was in the question. We want to produce 20 liters of the 6.2% solution, right? Okay. So, right, so again, if you like, you can try 10 and 10, right? Because 10 plus 10 is 20. And that usually doesn't work, right? So yeah, we're probably not going to divide this up evenly. It's not 10 liters of the 9%, 10 liters of the 5% to give you 20 liters of the 6.2%. And now one of these days it might be exactly half and half, but usually not, right? Okay, so of the X liters, right, of the 9% solution, how much is hydrochloric acid? 0.09 times X, right? If you like, right, if you have 10 liters of the 9% solution, right, what does that give you? That gives you 0.9 liters of pure hydrochloric acid. If you have 10 liters of the 5% solution, that gives you 0.5 liters of pure hydrochloric acid. When you add those up, you get 1.4 liters of hydrochloric acid. Now, is that what we want? So that's tricky, right? Because we're not told how much of the hydrochloric acid has to be pure hydrochloric acid. What we're looking for is 20 liters of 6.2%. So if we take 20 liters, right, 10 plus 10 is 20, and multiply by 0.062, do we get 1.4? So go to your calculator. Nope, we get 1.24, which is close, but it's not 1.4. It's not exactly what we need. So again, it's not half and half. It's a good guess, but that's not what we're looking for, right? All right, so going back to the table here, right? 5% of Y liters is 0.05 times Y. So that's how much pure hydrochloric acid is in the 5% solution, right? So now we can answer this a couple of ways, right? When we add these together, we're looking for, right, the 20 liters, but only 0.062% of, 0.062 of that is pure hydrochloric acid. So I think we did that calculation already, right? This is 1.24. Okay. So the top row is just the equation x plus y equals 20. The bottom equation is 0.09 times x plus 0.05 times y is equal to 1.24. And again, how did I get that? I multiplied 20 times 0.062. 6.2% as a decimal, 0.062. Right? All right, so those are the equations. Now on to step 3. Right? We have to solve this system of equations. And by now you should all be experts at this, right? You've done this many, many times. You can use substitution, or you can use the addition method. Either way, what I would do here, for the bottom equation, I would just multiply by 100, get rid of the decimals. You don't have to, but nobody likes fractions, and well, some people don't mind decimals. But if you don't like decimals, then just get rid of them. You get 9x plus 5y equals 124. Okay, so yep, no more decimals. Now we get nice whole numbers. All right, so now the only question is, do you want to eliminate x or do you want to eliminate y? So I just copy these down here. All right. Well, let's eliminate y. So to cancel the positive 5, we need a negative 5. So multiply by negative 5 on the first equation, both sides. So when you multiply both sides by negative 5, you get negative 5x minus 5y equals negative 100. And now the bottom equation, we can leave that alone. Add them up. Negative 5x plus 9x, that's supposed to be a 9, is 4 times x, right? Negative 5y plus 5y is 0y, or just 0. And negative 100 plus 124 is 24. So you can see we're almost done. If 4 times x is 24, divide by 4, x has to be 6. Right? Well, if x is 6, then we know what y is, right? Because x plus y equals 20, right? That was the original equation up here. But we know x is 6, so 20 minus 6 is 14. So, yep, x is 6, y is 14, right? And if the problem were just to solve the system of equations, you would have the ordered pair 6, 14, right? But that's not the answer in this case because we want to write it out as a statement in words. Let's see, we need x liters, so that's going to be 6 liters of the 9% solution and 14 liters of the 5% solution, right? So the chemist, and I know some of you are going to be taking chemistry pretty soon, so you might have to do this in your lab. So the chemist needs to mix 6 liters of the 9% solution with 14 liters of the 5% solution. Well, you can continue to obtain 20 liters of a 6.2% solution. I mean, that was in the question, but it doesn't hurt to be very clear about that, right? So that's the answer, right? And again, on a test, of course, I'll write everything down. You just need to fill in the blanks, the 6 and the 14. All right, so that's the first example. Just takes getting used to. And this is not easy at first, but if you go through it step by step here, and again, step 4 was just to answer the question, then you'll get used to it, right? But this is what I'm looking for on a test. And looking back, of course, it looks kind of sloppy here, but you know, I'm not looking for perfection. As long as it's legible, as long as I can read it, it's fine. All right, so that's our first example. On to the second one. All right, so I'm calling this example 2. How many quarts of water should be mixed with a 14% salt solution in order to obtain 56 quarts of a 10% salt solution? Okay, so that's the question. Again, so this is another mixture problem. Right? And what are we mixing? Well, we're mixing water and salt, right? Or a salt solution, right? So we want to know how many quarts of water do we need, right? So let x be the number of quarts of water. And what are we mixing? We're mixing it with a 14% salt solution. So let y be the, again, the amount, or specifically the number of quarts, the volume of this solution, of the 14%. salt solution. Okay, so we mix those together. These are mixed together, and what you should get is 56 quarts. The last problem was liters, right? So now we're using quarts. And of the 56 quarts, 10% of that is salt. So it's a 10% salt solution. Okay. All right, so that was our step one. Just declare the variables, make sure you understand the question, and write down what is x, what is y here. Right? Okay, so step two, we need the equations. And again, unless you get really good at this, the equations are not obvious. So let's make another table here. Okay. So what do we have? Well, we have water. And we're mixing that with a 14% salt solution. You know, if you're chemistry, you'll learn NaCl is the chemical abbreviation for salt, sodium chloride, right? I'll just call it salt. It's not necessary here. Right, and we mix those together, we want a 10% salt solution. Okay, so just to be clear, this is the mixture. Okay. Right, so what do we right, so what are we looking for, right? We're looking for the solution, and what's in the solution is salt, right? So pure salt. So for the solution we have, well, x quarts for water, y quarts of the 14% solution, and we want 56 quarts of the mixture. Got it? All right, so how much pure salt is in water? Well, let's be clear about this, right? This is pure water, right? Complete purified water, or sometimes called distilled water. There should be no salt in pure water. So that's 0, right? Well, 0%, right? So pure water, this is 0% salt, right? So 0 times x is, well, still 0. For the 14% salt solution, if we have y quarts of the solution, only 0.14 of that will be salt. So 0.14 times y. Okay, so we have 10%, so 0.10 times 56 quarts, that should be 5.6 quarts. So 5.6 quarts of essentially pure salt, right? Pure salt. So I hope that helps. Right? Step 3, we're going to solve the equations. So the equations are x plus y equals 56. For the second equation, we have 0x, which is just 0, and then 0.14 times y is equal to 5.6. Okay, so here we get a system of 2 equations in 2 variables. Step 3, solve this system. Oops, solve. And this should be easy, right? Remember, we're going to use the addition method. When you do the addition method, you eliminate either x or y. But notice that in the second equation, there is no x. So we don't have to bother with eliminating anything. We don't have to add anything. All we have to do to solve for y is to divide both sides by 0.14. 0.14, right? So we do that, and according to my calculator, 5.6 divided by 0.14 is exactly 40. 40 what? 40 liters? No, sorry, 40 quarts. 40 quarts. Okay. But that's just y. We also have to find x. So notice there is no x in the second equation. We have to go back to the first equation. The first equation was x plus y equals 56. But look, now we know what y is. Y is equal to 40. So to solve for x, take away 40 from both sides. X is going to be 16, right? So there we go, right? 16 quarts of x. What is x? X is the pure water. Okay, so we mix 16 quarts of water with 40 quarts of a 14%, yep, 14% salt solution. Right. To get 56 quarts of a 10% salt solution. And that should do it. Again, that was step 4. Just write down the answer as a statement. Again, practically, I'll leave these blank, and you just fill in the blanks. Okay. Right, so I hope that helps. You have 2 different types of problems for mixtures. And there's one more type of problem, and that's the motion problems. So I'll have to clear all this, and then we'll start with an example for a motion problem. You know what? I changed my mind. I think you should try one more mixture problem, and then we'll move on to the other type, the motion problem. All right, so again, try this on your own. The question is, how many liters of a 10% antifreeze solution and a 60% antifreeze solution should be mixed together to obtain 310 liters of a 50% antifreeze solution? Okay, so pause the video, try it, and then see what you get. All right, so hopefully step 1, you're going to say, let x be the amount or number of liters, so it's the volume, number of liters of the 10% solution. And we'll let y be the amount or the number of liters of the 60% solution. Right. Right. So step 2, make the table. So again, for the rows, we have the solution, and then we have what's in the solution. In this case, it's not salt. It's antifreeze. Is that clear? Antifreeze. Okay. And then for the columns, well, we have the solutions. We have a 10% solution. We're going to mix that with a 60% solution. And then we get something in between, a 50% solution. Right? Yeah, we do not get a 70% solution. You would need something way more concentrated, like pure antifreeze, to get something higher than 60%, right? Make sense? Yeah, so for the solution, we have x liters of the 10%, y liters of the 60%, and 310 liters of the mixture. So already we know x plus y has to be 310. But I'm getting ahead of myself, right? For the antifreeze, we have 10%, 0.10x, right? That's pure antifreeze, pure antifreeze. And then for 60%, we have 0.60 times y, right? And then in the third column, we have 50%, so 0.5 times 310 is, I think, 165. Yeah, half of 310. Oops. Oops, sorry, 155. Yeah, okay. Yeah, 155 liters of pure antifreeze. There we go. All right, so the equation 0.1x plus 0.6y equals 155. Okay. So whichever method you use to solve this, substitution or the addition method, again, I like to get rid of the decimals, so I multiplied by 10 here. You can multiply by 100, but it's not necessary. So here's the first equation. And then the second equation is going to be, well, 10 times 0.1, that's just x, plus 6y equals 1,550. So there's our system again, but this time with nice whole numbers. Right. And I think it'll be pretty easy to eliminate x. We don't want to add them because we would get x plus x is 2x. We need one of them to be negative. So just multiply the first equation by -1. Again, on both sides, right? So if you do that, you just get -x minus y equals -310. Add that to the second equation. And you get 0x, right, plus 5y equals, now I better use my calculator because I can't do this in my head. I know I should. I'm really bad at arithmetic here. 1240, 1,240. Okay. And now just divide by 5. And I want to say 248. So I should double check that. Yep, that looks right. All right, so 248. So that's y. Oops, sorry. All right, but we still have to find x. And if you remember, the first equation was just x plus y equals 310. But now we know what y is, 248. So take away 248, subtract 248 from both sides, and we get x equals 62. Right, so 310 minus 248. Yep, okay, 62, right? So that should do it. Now just answer the question. We're mixing well, here, right? So step 4. So the number of liters of the 10% solution is blank. And the number of liters of the 60% solution is blank, right? So you fill in the blanks, right? So for the 10%, 10% was x, right? So that's going to be 62 liters. Right? You can abbreviate L for liters. Right? And the 60% is y, so 248 liters. And that'll do it. All right, so I hope that helps. All right, so now we'll move on to motion problems. All right, so on to the next type of problem, right? This is a motion problem. Don't get confused with mixture. We're not mixing anything here. Here's what we have. We have a boat traveling down a river 66 miles in 3 hours going downstream with the current. Right? On the return trip, it only travels 42 miles going upstream, which is against the current, but in the same amount of time. Find the speed of the current and the speed of the boat if there was no current. Okay, so step one, we're going to let x. Oh, you know what? We don't have to use x and y here. We're looking for what? The speed of the current. So let c be the speed of the current. Right. Why am I not using s for speed? Well, we also need the speed of the boat. So if we used s, we'd have to use s for both. But b, let that be the speed of the boat. Right? With no current. Right. So on a lake, let's say. Let's try that again. No current. Okay. Okay. Right. So that's the first step. Write down your variables. Right. So you can use x and y if you like. I like to use b and c. It's more indicative of what we're looking for here, right? Step two, as always, build the table. Okay, so what do we have, right? We have this, we have the boat going, so it's not boat and current, right? We have the two situations. Read the problem carefully, right? We have the boat going downstream, right? Downstream means going with the current. Right, so this is going to be downstream. And, oh, I cut that off a little bit. There we go. And on the return trip, you're going against the current, so you're going upstream. Okay, so this is with the current. This is against the current. Right. Okay. Right. So what about the columns? The columns are going to be a little different in this case, right? For motion, for something moving, just think about what it means when you calculate the speed of something. Right, so what is speed? It's how fast you're going. It's the distance you travel, right, divided by the time. Right? But we're going to rewrite this slightly differently. If we multiply by time, we get that speed times time is equal to the distance. So that's the equation we need for our table here, right? This is speed times time equals distance. Right. Makes sense? I mean, let's think of it this way, right? Let's say you're in a, well, it doesn't have to be a boat, right? Let's say you're in a car that travels 40 miles per hour. And you take a trip that lasts for 5 hours. How far did you travel? Well, right, 40 times 5, right? That's 200 miles. Right? Does that make sense? 40 miles in the first hour, 80 miles for 2 hours, 120 miles for 3 hours, 160 miles for 4 hours, and 200 miles for 5 hours, right? So you're just multiplying the speed times the time, and that gives you distance. Okay, I hope that helps. All right, now for this particular situation, we have the speed of the boat, right? The speed of the boat, but it's going downstream, right? It's going with the current. So here's our little river here, right? This is going in this direction. You have your little boat here. Let's make it a little purple boat, right? And it's going this way, right? So if there was no current, the boat would be traveling at b miles per hour, right? But because the current is going in the same direction, it's dragging it along even faster, right? So what do? You add the speed of the boat plus the speed of the current, right? So the speed of the boat going with the current is b plus c. Does that make sense? Again, think of it this way. Let's say the boat can travel 20 miles per hour. I'm just making that up, right? That's not the answer. Let's say the current is 3 miles per hour. Again, that's probably not the answer, right? Well, right, if the boat is going 3 miles per hour faster than it normally would be going 20 miles per hour, the boat would be traveling 23 miles per hour, right, with the current. Right. On the other hand, let's say this is the current now. Let's say the boat wants to go the other way. Right. So now you're fighting the current. Right? So instead of going 23 miles per hour, right, you're going 20 miles per hour, but then you have to take away the 3. So you're only going 17 miles per hour against the current. Okay. So when you're going against the current, what do? You take the speed of the boat minus the speed of the current. Okay. So make sure you know the difference. With the current, right, this is again going downstream. You add the speeds. When you're going upstream against the current, you subtract. Okay, so now we can fill in the table, right? The speed of the boat going with the current, that's downstream, is b plus c. The speed of the boat going against the current, so that's upstream, b minus c. Okay? Now, how long did it take to go with the current downstream? That's in the problem, right? Right here, 3 hours. So 3 hours for the time. Okay. What about going upstream against the current? So against the current, it's the same amount of time, right? So it's still 3 hours. Same amount as going downstream, right? Right, what about the distance? So back to distance. So going downstream, 66 miles. So that's a distance. Right. Going upstream against the current, that was 42 miles. Okay. Right, there you go. So there's your table. And now we just need the equations. So to get the equations, I'm going to have to move this over. So, right, so we need, I just use that as my scrap work to get the b plus c and the b minus c. But just in case, I'm going to leave it there for now. Okay, so step 3 is we need to get the system of equations and then solve that system of equations. Right, so step 3, we need to solve. Well, the first equation is going to be b plus c times 3 is equal to 66. Right? For the second equation, we have b minus c, also times 3, is equal to 42. Right? So that's our system of two equations and two variables, right? So we could do one of two things here, right? You could multiply through by 3 here. So distribute the 3. Right? Nothing wrong with that. I would prefer to go the other way here, right? So the first equation is b plus c, right, times 3 equals 66. Since the 3 is multiplying both the b and the c, we can do the opposite. We can divide by 3 on both sides. And when we do that, we get b plus c is equal to 66 divided by 3 is 22. Okay. Do the same thing with the second equation. B minus c times 3 is equal to 42. Divide both sides. Well, let me do it in blue again, just to be consistent here. Divide by 3. 3 divided by 3 is 1, so they cancel. And now this equation becomes b minus c is equal to 42 divided by 3, 14. Right. So now those are our two equations. And let me just write them on top of each other here, right? So I'm just going to move this down here. And now you can see how easy this is going to be here, right? We don't have to multiply or divide by anything. All we have to do are add the two equations together, right? Because that'll eliminate c. So b plus b, right? Be careful. This is 1 times b plus 1 times b is 2 times b, right? This is 1 times c minus 1 times c. 1 minus 1 is 0, so 0 times c, right? And then 22 plus 14 is 36. Okay, so we eliminated c. We get 2 times b is equal to 36. So divide by 2, and b is going to be 18, right? And look, now that we know what b is, we can find c, right? b plus c is 22, so 18 plus c is 22. Subtract 18 from both sides. 22 minus 18 is 4. So we found b, we found c, and that's what we're looking for, right? The speed of the current, oops, I forgot what c is. C is 4 miles per hour, right? So this is just going to be 4 miles per hour. And then the speed of the boat is 18 miles per hour. 18, yes. Okay. So let's make this official. Step 4, right? The speed of the boat without a current is blank. You fill in the blank. The speed of the current is blank, right? So again, B for boat, again, this is the boat without a current, if there was no current, is 18 miles per hour. And you can abbreviate mph, miles per hour. You can also write miles divided by hours. That's the scientific way to write it, but either way is fine. And the speed of the current is 4 miles per hour. Okay. And so that answers the question. Okay. So yeah, a little trickier. Again, speed times time equals distance. This is the key because that tells you, right, that converts the table into the equations, right? You're not adding here, right? It's not b plus c plus 3 anymore. This is times now. Remember, when you're doing mixture problems, or if you're doing interest problems, you are adding, not multiplying. Here, you're multiplying, so be careful. Okay, so, right, so try the next one. Okay, next example. Flying with the wind, a pilot flew 600 miles in 4 hours. The return trip against the wind took 5 hours to fly the same distance. Find the speed of the plane with no wind, and find the speed of the wind. Okay, again, this is one you should try on your own now. Okay? So step 1, what are we looking for? Find the speed of the plane with no wind. Right? So let P be the speed of the plane with no wind. So on a calm day, I mean, there's always some wind, but let's say it's very calm. There's almost no wind, right? Right. And find the speed of the wind. Okay, so let W be the speed of the wind. Right. So it's the same situation we have, except instead of a current, it's wind, and instead of a boat, it's a plane. But it's the exact same idea, right? Exact same idea. So this is a motion problem, right? We're going to use a table here. Right. So we don't say upstream and downstream here. I guess we'll just say with the wind and against the wind. Okay, and then we have the same formula, right? Speed times time equals distance. There we go. So the speed of the plane is p, but if you're going with the wind, you're going to add the speed of the wind. Right? You're going in the same direction as the wind, so you're going faster. If you're flying the plane against the wind, you're going to slow down, right? The wind is going to slow you down. So P minus W. Right? The time, all right, so let's read the question carefully. The time, 4 hours going with the wind. So with the wind, time is 4. Right? The return trip going against the wind took 5 hours. So now this is going to be 5, right? Distance. Well, distance, we have 600 miles. That's going with the wind. Right? So 600 miles going with the wind. And then the same distance going against the wind. So that's also 600. Right? All right. So I hope that helps. You fill in the table, and then remember you're multiplying speed times time. So I'm going to use parentheses. P plus W times 4 is equal to 600. And then the second row becomes the second equation. P minus W times 5 equals 600. So those are our two equations, right? So you just solve this system. And if you use the same trick that I showed you last time, right, if we have P plus W times 4 is equal to 600, rather than distribute the 4, just divide by it. Right, so divide both sides by 4. And this becomes P plus W. Right, the 4's cancel on the left. 600 divided by 4 is 150. Right. For the bottom equation, we have 5 times P minus W equals 600. So now just divide by 5 on both sides. Right. 5 divided by 5 is 1, so you just get P minus W on the left, and 600 divided by 5, I think, is 120. Right? So 120. And there's our two equations again. Right. But at this point, this should be almost too easy. just add the equations together, right? P plus P is 2P. W minus W is 0. Oops, plus 0, right? And then 150 plus 120 is 270. So 2 times P is 270. Oops, 270. So just divide by 2. P is going to be 135. Okay. Now, how do we find W? Well, go back to the first equation. If we know P is 135, then 135 plus W is 150. Oops. Right? So just take away 135 from both sides. So that should give me W equals 15. All right, so we have P and W, right? P is what? P is the plane of the, P is the speed of the plane with no wind. Okay, so part 4, let's just answer the question. The speed of the plane without wind or with no wind is blank. And then the speed of the wind blank, right? So, yep, you go through this whole process. Step 1, step 2, step 3, and then step 4, just write down your answer. For the plane, it's 135 miles per hour, right? And then the speed of the wind is 15. So 15 miles per hour. And there we go. That solves the problem, right? That answers the question. So I hope this helps, right? And I know we're making this a little bit long, but you know what? Oh, I did 3 of the other type. Let's do 1 more of these. And hopefully this will be enough for you to do all the homework. Again, this takes a lot of practice, so don't get too discouraged if it takes a while here. Okay, last one. Right, so it's another boat problem. Again, plane, boat, same thing. Well, it's the same, right? You solve it the same way. Okay, so a boat travels 72 kilometers in 3 hours going with the current. In the same amount of time, it travels 48 kilometers against the current. Find the speed of the boat in still water and the speed of the current. Okay, so first step, what are we looking for? We're looking for the speed of the boat in still water. So I'll use a capital B. I think I used a lowercase b last time. Oh, it doesn't matter. All right, I'll stick with lowercase b. Sometimes they look like 6s, though. All right, I'll use capital B. So let capital B be the speed of the boat in still water. And that just means there's no current. It's all right with no current. Right. And they also, of course, want the speed of the current. So let's call that C. Let C be the speed of the current. I don't need the, sorry about that. Be the speed of the current. Okay. Great. Getting ahead of myself. Step 2, right? Table. Just make the table here. Right? Even if you don't think you need it, it doesn't take that long, right? So this is, again, speed times time equals distance for motion problems. Right, and we're going downstream, so that's with the current. And against the current, or upstream. Put the here. All right. Right. Right, so if you're going with the currents, let's see. You're taking the speed of the boat plus the speed of the current gives you the speed of the boat with the current. Right. The time, 3 hours. The distance, 72, not miles anymore, but kilometers. I mean, don't let that bother you, right? It's just a unit of distance, kilometers instead of miles, right? Yeah, so the speed of the boat going against the current, now you're going to be going slower, right? So speed of the boat minus the speed of the current. And it's the same amount of time, so still 3 hours, but now the distance is only 48 kilometers. Okay. So write down the equations. This is b plus c times 3. I'll put the 3 on the left, if that's okay with you, equals 72. The bottom equation is 3 times b minus c is equal to 48. Okay. So step 3, we have to solve this system of equations. And again, if you take my hint, just divide everything by 3 here. But let me show you, if you don't do that, if you multiply by the 3 here, right, and then here as well, you get the same thing. In this case, it's really not that much worse. You get 3b plus 3c is equal to 72, right? You're not multiplying the 72 times 3, right? There's no 3 on the right side here, right? In fact, you'd be dividing by 3, right? And for the second equation, you get 3b minus 3c equals 48. Okay, so this is fine. When you add the equations, you still eliminate c. So you still don't have to multiply by anything. Right. However, this wouldn't work in the previous problem because the previous problem had different times, right? We had, I think, 4 and 5 hours. So when these times are different, then you're going to have to start multiplying, right? But in this example here, when you add the equations, 3b plus 3b is 6b, 3c minus 3c is 0, well, 0c is 0, and then 72 plus 48 is 120, I think, yeah. So now just divide by 6. And that solves for b. Right, so b is, looks like 20. Right, 20, this, we'll get the units later, but it's kilometers per hour. Right. So that's the speed of the boat with no current, right? Yep. So that's 20 kilometers per hour. You can abbreviate it that way too. And now we need the speed of the current, right? But look, if 3 times b plus c equals 72, and again, we really should have divided by 3 first. That would have been slightly easier here. Oh boy, I can't do that in my head. So what's 72 divided by 3? I think it's 24. Yeah, 24 times 3 is 72. Okay, right. But we know what b is, right? b is 20. So subtract the 20 from both sides. C is 4, although that might seem like the same answer we got in the first problem. Remember, this is not miles per hour. This is kilometers per hour. So it's actually a different speed. And I don't know the conversion offhand, how many miles per hour that is. But you can look it up, right? But we're going to stick with kilometers here, right? So to answer the question, step 4, right, the speed of the boat is without a current, or let's say in still water, that's how they phrased it, is blank. And then the speed of the current blank. So speed of the boat is right here, right? 20 kilometers per hour. Right. And then the speed of the current, 4 kilometers per hour. So I hope this helps. It takes a little time to get used to it, but right. So that's all that you need for these types of motion problems, right? So yeah, and that's it, right? There's only going to be 4 types of problems in this section, right? The first type, I don't want to use, because this is step here, right? So the first type of problem is cost. So the cost of a ticket to a theater, the cost of a stock, right? So that's cost, right? And then the second type of problem was interest. So either you're borrowing money, I can't spell, sorry, interest. So you're borrowing money for a loan, or you're investing money in some sort of investment account, so savings account, or or bonds or stocks or whatever, but some sort of investment account, right? The third type of problem, these were the mixture problems. You're mixing 2 things, like salt and water, or hydrochloric acid, or fertilizer, or antifreeze, right? Just any 2 things you mix, right? And then the fourth type of problem is motion, right? Or if you prefer, just remember speed times time equals distance. So speed times time equals distance problems. So these are boats or planes. Boats or airplanes, right? Either moving with or against the current, or with or against the wind. Okay, so you should do at least two or three of each type. Okay, and I know each one takes 15, 20 minutes. That's how long it takes, right? But do at least 2 of each type, I would say. And I think that's generally how many there are in the homework. There might even be 3 or 4. So do as many as you can, right? As many as it takes for you to convince yourself that that you can do any problem that I throw at you. Any problem like this, if I give you a very similar example, I might just change the numbers. You should be able to answer the question. And again, you got to show all your work, right? Okay. All right, so that's it for this section. The next section is in the next chapter that has to do with exponents, so completely unrelated to this.